Welcome to the Brainwave. Today we are going to be talking about what is physics. So physics is this very abstract concept, and when people think of physics, they think of this very complicated thing that they will never be able to understand. But I promise you, physics is not that intense. The most intense part is understanding what matter is and what atoms are, and then once you get further into the subfields of physics is where it gets more complicated. But we're going to start things off pretty light. We're going to start with just what is physics and discussing some of the core concepts of physics and what we need to understand to be good physicists. And secondly, we're going to talk about measurements and significant figures and how to calculate significant figures. So let's go ahead and get started. So just generally, what is physics? Well, physics is technically the science of matter. So physics is anything to do with physical science in the natural world. So this has to do with the parts of matter, the motion of matter, the behavior of matter, the energy of matter, and the force of matter, and so on and so forth. It goes even deeper than that. Now, what's really interesting about physics is it is one of the oldest disciplines in science. So the ancient civilizations have been obsessed with physics and the stars and technological advancement for as long as we have recorded. There is not a time period that we have record of where they have not shown interest in physics. And now physics is even more complicated or obscure because the field just continues to grow. So as we get a new technological advancements, for example, quantum computing. Quantum computing is going to lead into its own entire branch of physics that we haven't even been able to think of, because quantum computers allows for superposition to be encoded into the computer. Now, if that doesn't make sense to you, it's okay. But basically it means that you can turn atoms on and say, instead of having this way or that way, I want you to do both at the same time, so they can be both up and down at the same time. So physics is still a continually growing field, but the main parts of physics are electricity, atoms, heat, light, force, magnetism, inertia, friction, gravity, and sounds. And as we go throughout the semester and throughout the year, we're going to hit on each of these topics individually, and hopefully you get a good understanding of how you can use physics to your advantage to solve problems in your own life. Now, the core of physics is matter, and the basic tenet of matter is the fact that matter is any object in the universe that has mass and volume. For matter to have mass and volume, it has to contain atoms, and an atom is the smallest unit of an element that makes up matter. So everything in the discernible universe is matter that we know of. The one exception, and we don't even know that this exists, would be something like dark matter or antimatter. They are technically different. We can hit on them later in the semester. But even that technically has mass, and the majority of the universe contains dark matter, antimatter, whatever you want to call it, and it's basically this invisible material or energy that we know is there and makes up, I believe, about 80%, if not more, of the universe, or that's our current prediction. We've never actually calculated it yet. But my point with this is that matter is the key to physics, and all matter contains atoms, and all atoms have some basic properties. And these atoms, which you guys should be familiar with already, but these atoms consist of what we call a nucleus. And this nucleus, think of it like the heart of a cell in biology. The nucleus contains the protons, which are the positively charged particles, and then the neutrons. The neutrons are the neutral particles. And then outside of our nucleus, think of my fist like the nucleus, we have what we call the electron cloud, or the electron orbitals. And these electrons are the negatively charged particles that basically fly around, if you want to think of it like that, but not really. Basically, they're attached. They're in a position relative to the nucleus. And as we get further into the semester, we may dive into particle physics and talk about quantum mechanics and how this model of the atom that you see here on the right of this screen is actually not that accurate. This is a very cartoon depiction. In actuality, the atom itself is always changing. So electrons are never singular. Electrons are actually waves, and all particles are waves. But this is the easiest way to conceptualize and try to help you understand it, and that's why we started depicting them like this. So this is one specific model of the atom. But all matter is made up of atoms. And so in order to understand matter and to understand physics, we have to be comfortable with the concept of an atom. Now, how can we measure an atom, something so incredibly tiny that we can't see? There's never a way in history that any of us, will ever be able to see an atom. The only way that we know atoms exist right now is because of particle colliders like the Large Hadron Collider, and also maybe scanning electron microscopes. But we can't see atoms with that. We can see chemical structures or finite molecules with a scanning electron microscope. So how can we measure what we can't see? And the reason I bring this up is because really the key to physics is the scientific method. And that's what's so unique about physics, is because of the ancient philosophers' interest in this core discipline for navigation and astronomy and understanding their own existence. Scientific method really came from this field. So there's some unique applications that we have to consider when we move into the world of physics. And the reason for that is because when we get to physics, we have to choose a model. And we'll talk about this more in a minute. But as we discussed the other day, the scientific method has essentially 5 main parts. You're going to make an observation. You're then going to form a hypothesis. You're going to figure out how you can test that hypothesis with experiments or math or some kind of theory that you may be able to form. You're then going to analyze the data, and then you're going to report your conclusions and start it all over again. Now, the key to the scientific method when it comes to physics is developing a model. This model can be literal, it can be something you can see in the physical world, or it can be mathematical. Now, the key to a model in physics is that it has to have a pattern, plan, or description to show how an object or system works. So, you may be thinking to yourself, why? Why does it need a model? You've never heard of this model before. In biology, we just do experiments and then analyze our data and make conclusions. We don't talk about a conceptual model. The model in physics is critical because typically the system we're working in physics is way too complicated. So we're going to use this basketball example down here on the right as our example. So in this example, we have basically a person that's shooting. So the person is one thing in our model or in our system. That's a giant confounding variable. The person's height can be variable. They can change over time. As they get older, right? They could get taller technically. Let's say they have long hair today, which is blocking their eyesight partially, but tomorrow they cut their head and they buzz it. That's a new variable to add in. Maybe they change their shoes. Their shoes are going to add a difference in their height. Maybe their shoes today are non-slip. Tomorrow they're wearing running shoes. That's another variable. Maybe today they're wearing heavier clothes than they will tomorrow. That's another variable. See, and we haven't even got to the ball. With the ball, the environment of the ball today will be different than tomorrow because the air temperature could change. Maybe the ball gets greased tomorrow. The ball size could change tomorrow. The spin on the ball could change as the person shoots it. The weight of the ball could change day to day. The color of the ball could change, which may change the person's perception, so on and so forth. So this is the problem with physics. When we're trying to analyze something as small as the matter that makes up all of the universe, the world gets really complicated really, really quickly. So we, as the physicist, as the scientist involved in these experiments, have to decide what is important and what can be ignored. So this is how we build our models in physics. We have to know what is the key fundamental thing at this exact moment in time that I'm trying to record and understand. Okay, I can't understand 47 things at once. Our brain just can't do it. We don't have the math for it, and even computers cannot compute it. Okay, maybe once we get quantum computers, because then we can essentially create exact replicas of the entire world and the entire universe, but that's a problem and a question for a different day. So with these models, the first step really is to define the system. So for example, with our basketball player over here, in this example, I don't really care what color the ball is. I know that affects the shooter, but I can take the shooter out of the equation. So let's say that we decide we're going to build a simple machine to replicate the shot over and over again, and we can simply adjust the arc of the shot or the trajectory of the shot as well as the speed of the shot, so the force behind it. At that point, we've taken the shooter out of the equation, so we're defining our system. So we have to determine what objects or particles in the experiment we're doing are going to impact the focus of the study, and then we're going to disregard the little stuff like the shooter, his clothes or her clothes that she's wearing, her shoes that she's wearing, the color of the ball, the angle of her wrist, all of those things. We're going to try to negate them. We're going to try to get rid of them because what we're trying to understand in this example is how the ball moves through space and time in order to make the perfect basketball shot. So that's step one. We have to define the system. I've got to know what's important right now. Step two, we're going to form a hypothesis. So if you're noticing here, we're going through the scientific method, but physics just has a couple more steps. Step two, form a hypothesis. We're going to create a reasonable explanation for the observation, and we're going to try to make that testable. So with our hypothesis for the basketball shooter, for example, we notice, for example, that the basket that we're trying to aim in is parallel to the floor, so it runs even with the floor. Therefore, if I'm standing here, I have a machine here, and I try to just shoot directly at it, I'm most likely going to hit the rim. I'm not going to go into the basket. Okay, so the logical hypothesis is that if I add an arc to the basketball and try to get it over the rim, I have a higher probability or a higher chance that the ball will go into the rim. Okay, so that is our hypothesis. Our hypothesis is that by putting an arc on the shot, we should be able to increase the likelihood or increase the chance that the basketball will go through the basket. Okay, so now we've done step two, we formed a hypothesis. Now we're going to try to perform a controlled experiment. So in this example, we're going to try to perform an experiment or design an experiment that tests the thing we're interested in. In this case, we're interested in making the ball into the basket and what kind of math or trajectory we may need to take. So we're going to figure out how we can shoot the ball using a simple machine at different angles to determine which angle may be the best for our shot. Or for shooting generally. So to start, what we're going to do is have our basket here, we're going to have a simple machine here, and we're going to shoot the ball directly at the hoop, basically as a control group. So we're going to have a control group that is essentially a zero in this case, or a negative control, because it's most likely not going to go in if we shoot with a flat trajectory. After that, maybe we angle the machine back by 5 degrees, and we shoot 10 shots, and we take a chance, or we try to see what the probability that the ball will go into the hoop is at a 5-degree angle. And then we're going to go to 10 degrees, and then maybe 20 degrees, then 30 degrees, then 40, then 50, then 60, then 70, and so on and so forth. And we're going to record the number of successful shots or successful attempts at each angle, and then compare that to our control group, which is our zero. So that is our controlled experiment as part of our scientific method here to figure out how to properly shoot a basketball. Now, once we performed our controlled experiment, we're going to go on to step 4 and 5, which is to analyze our data. So we've recorded the number of successful attempts or successful shots, and then we're going to calculate a statistic, which would give us what we call a p-value. A p-value is essentially the probability that the event that occurred by chance. If an event occurs by chance, we want that chance that it was a random event to be less than 5%, basically saying that you are 95% confident in your outcome, and that would tell us which of our angles of our shot would be the best to practice basketball on, so that we know what the best shooting form may be. Now, of course, this is a simplified experiment, right? Because we set our system as what is the perfect angle to make it in the basket. We have negated the variable of the human. So now you have to go from your simple machine to start adding some of the variables back in for the human. And that's why when we talk about the scientific method, we talk about this circle over here on the right, where once even after we've reported our conclusions, we then make a new observation. So I go, oh no, my simple machine, it worked absolutely perfectly, but now I have to worry about the person's bending their knee and loading up their spring basically to shoot. How does that affect my arc? or how does that affect my trajectory? Because now they've increased their height as well as the force behind the ball. So I've added two new variables that I wasn't accounted for with my simple machine. So how do I adjust my experiment to account for those new variables and tell or determine what the best trajectory for my shot would be? So basically what we're getting at is that physics has rules and relationships, okay? Just as everything in the universe has rules and relationships. And as we go through physics, we will talk about this and try to understand really at the core what the physical world is, as well as how to operate and work through it so that you guys can be the best problem solvers that you can be. And this is really the core concept here, is we need to understand the scientific method because physics is entirely based on the understanding of the scientific method as well as the understanding of matter itself. So we will work from big to small. We're going to start with simple things like motion, and then we'll move into more complicated concepts in the spring like nuclear physics and electricity, where we get more abstract. Now, we're talking a lot about experiments here and the scientific method. And with all these experiments, we have to take some kind of record of the result for each of these experiments. And these records of our results are what we call measurements. So in physics, and in many sciences, any kind of physical science, we take numerical measurements. Now, numerical measurements are technically different. I know the name sounds the same as what you would have in math, but numerical measurements are technically different than what we have in math, because in math, for example, if I have 2 plus 2 equals 4, that is an equation with random integers included. The 2's are the random integers, and that gives me a product or a result, which is the 4. Now, in a numerical measurement, basically what we have is two distinct things that have to be included. Okay, we have to have a description of what kind of physical quantity is being represented, and this is what we call the dimensionality of the data, or the dimension of the data. This is things like length or mass or the force or the energy contained in a particle. And then we also have to have a description of the physical quantity. So these are our units. These would be things like grams or meters or seconds. So if I say the length of my car is 6 meters, okay, that is very descriptive. Whereas in math, I technically could just say that I have a vehicle that is 6. Okay, and that I understand that that's illogical because you're thinking to yourself, well, what about word problems where we're going to have those details? But that is not always how math works, because math and physics itself, but math is a language. Okay, so if you talk to people who are mathematicians, like hardcore mathematicians, they don't need units. They typically find the quickest way to cancel out the units, and they work with just the numbers or just the symbols that they need, because they're reading a language and then trying to write into the language. Whereas we are using the language of math to describe what is happening in the physical world. So we need to make sure all of our measurements are precise, accurate, and have these descriptors every single time. And dimension and unit are similar. I understand that they probably look similar to you right now, but I promise you that they're different. And it's very important that your dimension aligns with your unit. For example, I can't tell you that the length of my car is 6 seconds. That wouldn't be logical. There would be no way for you to work through a physics problem if I said the length of the car is 6 seconds. Because, for example, let's think about it as distance equals rate times time. I gave you a time, but I didn't give you a speed or a velocity at which the car is traveling, and therefore you can't calculate the distance of the vehicle. So in order for you to make sense of physical space and physical science, you have to have dimension and unit in unison. They have to work together, and you require both to be able to properly do your problems and to understand the world. Now, because we need to have both dimensions and units, we have what we call Sisteme International de Units. SI units. And you should have talked about these before in other classes, but this is basically a system that scientists have agreed upon to communicate our results. So we have 7 base units. These are things like length, mass, time, amps for electricity, Kelvin for temperature, moles for the amount of a substance if we're talking about elements or particles. And then we also use prefixes to fit in the extremes. So from chemistry, you should be familiar with nanograms, picograms, micrograms, centigrams. So there's 100 centimeters to a meter. So those are unit conversions. And we have conversion factors, which are shown on this chart on the bottom left. And we will go through these and make sure everybody's comfortable with them. But we're going to get very, very familiar with these units of measurements and how to convert them and work with them. Now, quickly we need to hit on accuracy versus precision because they are similar in concept but different in application. And the reason for that is that no measurement is perfect. Everything that you do has error in it. Even if you went just as simple as, oh, when I put my shoes on today, I did it differently than I did it yesterday. Technically, if you have a routine and you count that routine as being a measurement, you will never be perfect on that measurement. You will always do something slightly different. And so we need to be able to account for the errors in our ways because we are human. We make mistakes. That's just how it works. So we have 2 kinds of error that we account for: method errors and instrument errors. And statistically, we technically have 3 different types of error: type 1, type 2, type 3. We'll get into those later in the semester. When we talk about a method error, we're talking about basically choosing an incorrect method. So, for example, I need to measure the temperature of boiling water, and instead of using a thermometer, I used a meter stick. That is a measurement method error. I chose the wrong tool to do the job. Whereas an instrument error, so the first type of error is a method error. So this is basically I chose the wrong method to do something. So let's say I need to take the temperature of the water, of boiling water. Instead of using a thermometer, I'm going to count how long it takes for the water to boil. That doesn't tell me what temperature the water boils at, so I've used the incorrect measurement or method to calculate the boiling temperature of water or the boiling point of water. Whereas an instrument error would be that essentially I have an instrument that is not certain enough. So let's say I have 2 options. I have an analog thermometer and a digital thermometer. Let's say I choose the analog thermometer, but I can only read within 0.1 degrees Celsius of certainty of my thermometer, but with my digital thermometer I could have got within 0.001 degrees Celsius of certainty of my thermometer. So the digital thermometer is more precise than the analog thermometer, and in that case I technically made an instrument error by choosing the wrong tool to take my measurements. Now, this goes into accuracy versus precision because accuracy is how close a measurement is to the correct measurement. So this is basically saying, did I do a good job? Okay, so if I measure the amount of water in here as 47 milliliters and it's 47.9 millimeters or milliliters, I'm close, but I'm almost off by a milliliter, and in that case I have a decent amount or a large amount of error in my measurement. Whereas precision is the level of exactness of a measurement. So how exact is your instrument? So let's say rather than eyeballing it, I have a volumetric flask or something, or let's go less specific than that. We'll say I have a graduated cylinder. So I have a graduated cylinder that's calibrated down to 0.000001 of accuracy or of precision, excuse me. And I pour the water in there and I get a measurement of 47 milliliters of water out of this cup, and then I compare that to another tool, another graduated cylinder, and I get 47.1 milliliters of water, we can say that I am highly precise in my measurements of this water. So the exactness of my measurements is very close or very comparable to the other, which would give us a high precision and a high accuracy. So I know this is kind of an abstract concept, and it's something that you maybe haven't thought of before, but I think this diagram on the right is an easy way to explain it. So we'll start over on the bottom right side here. So in this one, you'll notice that we have high accuracy but low precision. So you'll notice when we're talking about accuracy, you see all of the dots here are towards the center. So we have a good clustering of the dots, but they're not right on top of each other. So when we're getting close, when we're getting close to the correct measurement but not exactly on it every single time, we say that that's highly accurate but low precision. If we move to the bottom left here, you see that we have low precision and low accuracy. The dots are all over the place and they're not even close to on top of each other, so there's no accuracy and no precision. If we move up to the top left of this diagram, you see we have high precision and low accuracy. The goal here is to hit the bullseye, and the cluster of our dots are completely off of the bullseye. So we're off of our correct measurement. However, the exactness of our measurement over and over again is right on top of each other. Our dots and our measurement are almost exactly the same every single time. And then if we move in the top right corner, this is where we want to be every time. We want to have high precision and high accuracy. So we have high accuracy because the goal is to hit the bullseye, and all of our dots are on the bullseye. And then we also have high precision because all of our dots are on the bullseye. So this is the perfect world where we are hitting our target as close and as exact as we can be, and on top of that our measurement is as exact as possible. So we're using the right tools and getting as close to the right measurement as possible. So when we're talking about accuracy and precision, we track the imperfections and the imprecision of our measurements using what we call significant figures. So these significant figures are the number of digits that measure the certainty and uncertainty in our measurement. So for example, if I put a weight like this cup, for example, on a scale and it measures out to 0.4544 grams. The 0.45 grams is the certain amount of measurement. Those are our significant digits that we are certain of. And then the 0.0044 grams, we would say are our uncertain digits, and the one we would count would be the 0.454. So we'd count one of those uncertain digits as our significant figures. And so this exact measurement, this type of measurement would have 3 significant figures, and we'd cut off the last 4 there. So we use these significant figures as a way of ensuring that things are going well and that we're accounting for the imperfections in our measurements. And this is a very common practice. So for example, if you're measuring off of a graduated cylinder, it probably is going to be in increments of 1 milliliter. But in like a college class, for example, and I will make you do this too, you're supposed to estimate the additional significant figure. So if you read off that you have 45.1 milliliters of water, I'm going to ask you to write down 45.1 and then an estimated figure, so 45.12 milliliters of water. And the reason for that is so that you can account for the uncertainty in your measurements, because I highly doubt that you were perfect enough to get it exactly on the line of that graduated cylinder. And this is not some kind of woo-woo thing we're just adding. This is how it is done everywhere in the world. So we're going to learn and be taught in the way of science, in the way of SI units globally. Now, these significant figures. Okay, hopefully this isn't a new topic, but if it is, this can be kind of scary because there's more math and more concepts involved in it. So there are certain rules that you have to follow when you're determining the number of significant figures. So for examples, if you have zeros in your figures, there's a whole set of rules that you need to follow. So like on this top one, it says zeros between other non-zero digits are significant. So for example, if my measurement is 4.015 seconds, which would mean that my stopwatch is capable of reading 4.01 seconds, and I estimated the 0.00 5 of the seconds, that would mean I have 4 significant figures there. If I have zeros in front of non-zero digits, those are not significant. So in this example on the right, I have 0.007 seconds. In that case, these 3 zeros on the left of the 7 are not significant, and I only have one significant figure, which is the 7. If there are zeros that are on the end of a number and right of the decimal, they are significant. So for example, here we have 57.00 grams. So we have 4 significant figures there. The 5 and the 7 on the left of the decimal count, and then the 2 zeros, because we have recorded them, also count on the right of the decimal. Zeros at the end of a number, but to the left of the decimal, are significant if they were measured or estimated. So this is a rule that changes on who you're talking to, or depending on what world you're working in. So my example over here on the right is 10 meters. So 10 meters, depending on what digit you estimate. If you actually measured out 10 meters, then you would estimate one additional digit, which would be like 10.01 or 10.1, whatever you think it is. And at that point, you could estimate it, or not estimate it, excuse me, you could round it down to 10 meters, and in that case you would have 2 significant figures. I know that's complicated, I'll explain it more in person. Then for the other way to think about it is, because you measured 10 meters exact, you also only have one significant figure there, so you could write that as scientific notation as 1 times 10 to the first, and that would be one significant figure. So this one is a complicated one, and like I said, we'll discuss it more in class and go over it so make sure everyone understands it. But this one is an either-or situation. The key here is to be consistent in the way that we do it, so we will lay out rules as a class. Now, when you're working with significant figures and we're doing math and talking about mental models or mathematical models, we very commonly are going to have to do some operations on these, so addition and subtraction, or multiplication and division. And when we add and subtract things with significant figures, it's pretty simple because you add and subtract in columns. So for example, if I have 94.22 plus 5.52, you can see that clearly the 9 would be in its own column, but you would have 4 plus 5 and then 22.22 plus 0.52. So that total would equal to 99.74. And then we would estimate and basically keep the round down to the total number or the smallest number of significant digits. So you'll see we have 94.22 has 4 significant figures, and then 5.52 has 3. So our actual answer here would be 99.7. So we'd get rid of the 4 on the end there, and it would just have 3 significant figures at the end. And then if we multiply or divide, we have the same significant figures as the number with the smallest significant figures. So in our example here, we have 114 times 5.22, which would equal to 595.08. Okay, so if we look at our two numbers that we put into our equation here, we have 114, so that's 1, 2, and 3 significant figures. And then we also have 5.22, which is 1, 2, and 3 significant figures. So our final answer only needs to have 3 significant figures. So in our result though, we got 595.08. That's technically 5 significant figures. So we're going to have to round down to get to our 3 significant figures that we need to report as our answer. So here we're going to round down to 595, which would give us our 3 significant figures. So I hope that made a little bit of sense. I know this is kind of just an easy start to the semester, but we will go over this more in depth. We'll do some practice problems during our first lab this week. If you have any questions at all, please feel free to reach out. I hope you have a wonderful day. Thank you for your time, your energy, your effort, and I'll see you next time.